I hope you enjoyed the first day, and we're going to start with the first speaker of the day. So it's my great pleasure to introduce Tinne, and I'm probably going to mess up the name, but Tinne Tuytelaars. She's a full professor at Katholische Universiteit Leuven, and part of the PSI Vision and Speech Processing Group, and her research focuses on computer vision and continual learning, covering topics such as robust image and video representation, object and action recognition, multimodal analysis, and image and video understanding. She received the Conjuring Test of Time Award in 2016 for fundamental contribution in computer vision, and she was a general co-chair and program co-chair for CVPR, and an associate editor-in-chief for PAMI. And with that, I'll give her the floor, and yeah, let's welcome the first talk.
Okay, everyone can hear me? Also remotely? I don't see any complaints, so I think it's fine. So yeah, I'm glad to be here. Thanks to the organizers for organizing this great conference and for inviting me. Thanks to all of you for waking up early and letting the rain deter you from coming here. My talk today is not going to be very technical. It's still early in the morning. Rather than a very technical talk, I'd rather reflect a bit about some concerns I have, some things I guess we might be doing better or differently in the continual learning community, specifically related to reconsidering continual learning setups. But I realize I haven't shared my screen yet. So let me see if this works. Okay. So before diving into this topic, maybe a few words about me and my lab. I guess the list of topics that Rastan mentioned were like more relevant a few years ago in the meeting. I guess these are the 4 topics that I mostly work on. So I have a team of 12 or now maybe 15 researchers, mostly PhD students, and they work mostly on one of these 4 topics. And so at first they might seem rather disconnected. We don't really integrate them yet. They're like different people working on different topics. But in my vision, they actually all should come together sooner or later. We've already seen a couple of talks. People looked at the combination of self-supervised learning and continual learning. So I guess that's a logical mix. If we can learn better representations without labels that are not task-specific, but that are more universal, then that will definitely help to generalize to new tasks that will allow us to do better continual learning. And especially it will allow us to hook up an agent to a stream of data without needing to have a human in the loop to do the actual annotations of all that data. That is also obvious. At the same time, I think there's a lot of potential if this unsupervised data that we learn from could also be multimodal. If we can combine multiple modalities, the co-occurrences between these modalities give us really strong cues to actually get to the semantics. And especially if we look at the combination of images and text, I think that there's a lot to be gained, because if we have text, that brings more structure to the data. And so if we learn representations purely from analyzing data, if we can do so by also having text as well as images, then getting meaningful representations is a lot easier. So a nice example of this combination of multimodal learning and self-supervised learning is a model like CLIP, but we haven't seen a lot of multimodal self-supervised continual learning yet. I guess that's one of the next steps. And then there's this last block, dynamic architectures, that seems like the furthest away from these, and I haven't heard much about that yet. But in my view, it also fits in the bigger picture, because with dynamic architectures, what we try to do is to make models adapt, to make them more flexible to the actual input. The main difference is that if you do continual learning, we want models to adapt at training time. And so the focus is on how we can learn better models dealing with different distribution shifts. With dynamic architectures, we focus on at inference time. So at inference time, we don't want to just deploy the same module, but we want to adapt it, have different modules analyzing the image depending on what the image looks like, or analyzing different parts of the image differently and things like that. And so far, dynamic architectures has mostly been focused on efficiency, trying to speed up the inference process. But there's like potential of bringing some of these ideas also, combining them with continual learning, because if we have different modules in our network, that can also benefit when we want to learn and not forget and things like that. So within a couple of years, I hope that these different research domains, which now are still mostly separate, will merge and come together. And that will bring us to something like this. So that's my mental picture if I think about continual learning. We want to have an agent that we can just hook up to a stream of data. It can just television or YouTube or whatever. And by analyzing this data, it can learn and it can get better and better at this task. Now, the Neal system that Abhinav talked about yesterday might be a good example of that. But then he said, like, well, actually, I don't believe in this setup anymore because it lacks the active component. We need to have an active component as well if we want to really build intelligent agents. I kind of disagree there. I think it depends on what you want to do. If you want to build an agent that can grasp objects and interact with the environment, then definitely you need to have this active component. But also in the human brain, the pathway for motoric skills is very different from the pathway for more semantics and understanding. And so I guess there's a lot of things we can do if we just want to have a conversation with an agent. If you want it to understand what's going on around it, then probably we don't really need this component. And by leaving it out, it just simplifies so much. Having the active component, you have to deal with the batteries of these robots running out and moving the robot from one location to the other and things like that. So for me, just passive would be good enough, and I guess we can already get pretty far with that. Now, this is my personal view of continual learning and where I think we should go with this field, but I realize it's just one of many views on continual learning. And other people may have a very different motivation for looking at continual learning and approach it from a very different angle. And I just listed a couple of them over here, but the list is by far not exhaustive. On the one hand, you have people who are like intrigued by continual learning as a step towards artificial general intelligence. They want to make agents that can learn like babies, that are like biology inspired or mimic some of the biological systems and processes. And that motivates them to look at continual learning. Then you may have other people who are motivated by scalability. They want to build bigger and bigger systems processing more and more data. And if you're consistent and you think about ever-growing amounts of data, ultimately an infinite amount of data, then you end up with continual learning. But it's a very different view on what continual learning is. And that means that there might be different constraints, different assumptions, different goals that they have in mind. Other people may be more practical. They may be working in a big company that has to retrain their models from scratch. every so often, and that's not very durable. That's a lot of waste of resources, and so they want to have a model to avoid this recomputing from scratch. Other people may be working on reinforcement learning or robotics, a context where the data is inherently non-stationary, because the data is on the actions taken by the robot or the agent. And there's no way you can avoid it in the first place. And then you have people who are thinking about continual learning as a way to get personalization and adaptation. Often they have in mind a system that can run on the edge, where you have like just on your mobile phone, on a robot, on a smart camera, with very limited resources, where you cannot store a lot of data, you cannot have really huge models, but still you want to be able to adapt and personalize. And so what I feel is that as a community, we are never explicit about all these different views on continual learning. And we have different constraints, assumptions, and goals because of that, but they're left implicit. And so in a paper, you don't really find it immediately like, is it this or is it this? And people criticize other papers because maybe the way they tackled something is not really fitting their view on learning, but we should just be clear about this and try to formalize it better. And I guess that's one of the main messages I want to give with this talk. Maybe we should really think about, as a community, how we can make this all more formal and more explicit, have the right terminology so that we can really distinguish between these different views on continual learning, and it's not like a melt pot where it all is put together, which can be confusing, like lead to criticism or makes it less clear really what we're after. Just as a few examples, for some of these settings, it may be very logical to use large pre-trained models. If you just want to avoid recomputing, then just take a large model, the best you can get, and build on top of that. On the other hand, in some of the other scenarios, this doesn't work, and it's just a no-go to assume that you can start from a large pre-trained model. You want to learn from scratch, just like a baby does. Likewise, in some settings, if you have this large pre-trained model, you can assume that, or the best thing you can do is just freeze the feature extraction. Just learn the classification head, maybe learn a bit of prompting at the start, but not change the feature extractions. For some settings, that's the best thing you can do. There's no forgetting about the feature stations, and it all works very well. Yet a lot of other people will say, like, well, that's not continual learning, because the key of continual learning is really to make sure that we can keep on learning, we can improve our feature extractor. If we freeze it, then there's nothing we can learn over time. And finally, there's the issue about storing samples or having access to old data. Some settings say, like, no, this is a no-go. You shouldn't have access to old data. But in practice, often storage is quite cheap, and the data is available somewhere, maybe not directly on the memory on your GPU, but having the data available is not such a big cost. And so it's another example where basically we are not explicit on what we want, what are the constraints, and I think that's not a good thing to have. Okay. Now, if there's one thing that is kind of agree upon, in spite of the different motivations we have, then it seems to be that we want to go beyond solving data sets. It's like the one thing, like, oh, traditional machine learning is bad because they're just focusing on solving data sets or maybe solving a particular data distribution, and then you overfit and you don't generalize and you cannot deal with domain shifts and so on. And so that's something we're all agreeing on. At the same time, I want to push back on this a bit, because sets by themselves have a lot of merit. It's thanks to the fact that we had something like ImageNet that a field like computer vision could make such a progress over time. Because having a fixed data set means that you can compare different methods, you can measure your progress, you can reproduce results. Coming back to the example from this never-ending learning, like this NEAL system that Abhinav mentioned, suppose that tomorrow someone with a new version of NEAL that builds on the latest advances in continual learning. How could we compare this NEAL 2 with the original NEAL? There's no way we can really tell whether this is better or not, because it's trained on different data. We don't have anything to build on. And so in that sense, it may be a bit controversial that although we say like, we all want to go beyond solving data sets, and that thing we agree on, at the same time, I want to advocate that we need data sets, we need to have benchmarks, we need to have like at least experimental setups that we work with, again, that make explicit what are the constraints, what are the goals, what are the assumptions, and so we might have different setups for different people with different like views on continual learning. But this is key to make progress, to measure progress, and to really bring structure in the field. And so that's basically the second message I want to bring. To make that a bit more clear, I want to zoom in on what probably is the one experimental setup or framework that has been used the most within continual learning, but that also these days has been criticized quite a lot. And that's basically this task-based sequential learning. So this is a slide over the last few years I had in almost any talk on continual learning, explaining if we want to do continual learning, how do we do that? Well, we actually have different learning episodes. During one learning episode, we learn one task based on one data set. After that, we can solve that task. We throw away the data of the old task. We load the data of a new task. We learn the new task. But then at the end, we evaluate not only on the new task, but also on the old task. And so that's where we hope that we can learn and we can expand our knowledge by adding more and more tasks until we get some really powerful system. And you're all familiar with a few variants of this scheme. This is task incremental learning. We can also say, like, in one learning episode, we are exposed to a certain set of classes, and then we move to another set of classes and another set of classes, and then we have the class incremental setting. Or we have the domain incremental setting, where we want to solve just a single task, but the context changes. So an example of task incremental learning could be like something like learning different sports. You can play tennis, or you can play badminton or table tennis. But you learn one task after the other, and it's clear which task you basically need to solve at any given time during inference. Class incremental might be first you learn about domestic animals, like distinguishing between cats and dogs. Then you learn about farm animals, and you have to distinguish between horses and cows or something like that. And domain incremental is something where you could, for instance, say, okay, I want to drive my car, or I want to build a self-driving car, but it has to be able to do so not only under nice weather conditions, but also at night, also when it rains. And so we have different learning episodes where we have different contexts, different imaging conditions to which we expose these things. And this is how these three different setups are typically interpreted. Just giving a few examples, and intuitively that makes sense, and we're all happy about this. But at the same time, we're actually pretty sloppy in how we define this. And then what is it really that makes a difference between a domain-incremental setting and a class-incremental setting? What's a task, actually? And so Guido, who's like here in the audience, Guido van de Ven, together with his supervisor, Andreas Tuytelaars, was the one who introduced these three different scenarios. But then they continued trying to make it more formal, to make it more explicit. What does it really mean to be class, task, or domain incremental? And then when Guido joined my lab, I also got involved on this. And so we're working on this together, trying to make it more formal, more precise, so that we can actually, we know what we are talking about, and we avoid a lot of the confusion that there is nowadays. For instance, a lot of people would agree with a statement like this, that it's primarily the data set that determines the scenario you're in. If you work on split MNIST, then you're probably doing class incremental learning. If you're working on images and sketches like domain-net, then you're probably doing domain incremental learning. And so the data set seems to be the key that determines the scenario. Well, actually, that's not true. I'll show later in this talk that this statement is actually false. Likewise, we don't have a proper definition of task. A task can, even when we have the class incremental setting, we talk about different tasks, and a task then seems to be a learning episode. But at the same time, people say that you can revisit tasks, and then task cannot just be a learning episode, because then at a later learning episode, you revisit what? So again, we need to have more tight, more formal definitions of all these things. So next, I'll have a few slides that maybe some of you might recognize, because Guido already had a talk on this in the online, virtual part of CoLLAs. But I'll just go over it because I guess that it nicely illustrates the point I'm trying to make. So where we try to look at continual learning in a bit more formal fashion, not this sloppy, intuitive thing like giving examples to explain what is what, but trying to have it like really mathematically defined, which yeah, but like there's not much interaction between them and but so I think it should be people should be more aware of this, and people should adopt this, and so indeed there's a lot of theory, but it's not used, or people don't build on it, and people use terms and define things that are not very crisp. Okay, so if we say we want to do continual learning, we have to basically set it apart from classical machine learning. And so in classical learning, basically what we want to do is learn a mapping that maps an input to an output based on some training data. Training data is basically samples drawn from a joint distribution of inputs and outputs. And in classical machine learning, we assume that this is like a stationary distribution. In continual learning, there's two key differences. That is, the training data arrives incrementally, and the distributions can shift. So, purely thinking about it as distributions that shift, we can already try to categorize continual learning problems, because the way that you have this non-stationarity, the aspect of the data that changes over time, can relate to the mapping that you learn in different ways. And so thinking about it like this, we end up again with domain-incremental, class-incremental, task-incremental, from a more formal definition, a more formal point of view. Also, before we go there, I want to stress that there's one assumption that I guess most of the people, again, in like the continual learning field, like most of the papers or talks we've seen here at this conference, make this assumption that there's no concept drift, but rarely make it explicit. So we assume that if one image has a certain output, so for instance, this is an image of a cat, then also later in time, that same image will still be mapped to the same label. An image that's a cat is not suddenly going to be an image labeled as a dog later on in time. This is a key assumption. There's lots of applications where this is not valid. If you have something like where you want to predict the popularity of a movie, for instance, that might change over time. If you want to do continual learning in that kind of scenario, you have to build on something where you allow for asymptotic forgetting, that new data can override old data. In our setting and in most of the papers on continual learning presented at this conference, there's no concept drift, and so we have to be explicit about that. Okay, so I said like we want to categorize your learning by looking at how the non-stationarity is linked to the mapping we want to learn. We start by explaining this for the easiest case, that is, we have just a classification problem, and we have different episodes that are learned sequentially, similar like the example I gave earlier. And there's no overlap between episodes. Again, no overlap between episodes is not really very crisp. What we mean is both temporally, episodes do not overlap, but also in terms of the distributions, they do not overlap. Often these episodes are referred to as tasks, but as I indicated earlier, we think that task should not be used in this setting. Here it's rather something we call context. The context refers to a certain distribution from which we sample, and the context is what changes over time. The distributions change over time. The tasks may remain the same, or they can ditch. So for instance, you can have split MNIST, where you have different contexts, like distinguishing between 0 and 1, 2 and 3, 4 and 5, and so on. And sample then consists of an input, a within context label, and a context label. And then you can actually distinguish 3 different settings. First, you can assume that you know the context you're in. You have access to the context label, and so your input is not only image, but also the context label, and from there you want to map to the output. Or you can have a setting where the context label is not known, but actually you don't care. You only want to predict the within context label y, and so the context is kind of a hidden variable, a latent variable that is not really relevant. Or you can have the third setting where you don't know the context label initially, but you have to predict it, you have to tell what it is. And so these 3 different settings can be applied to our example of split MNIST, where in the first setting, we always want to just distinguish between 2 digits, like between 0 and 1, or between 2 and 3, or between 4 and 5. The second setting, we don't know the context, but we don't care. For instance, we only want to distinguish between odd and even digits. And the third setting, we want to predict both the context and the label, which basically means we want to distinguish between all the 10 digits. And so then it doesn't come as a surprise that basically this corresponds indeed to this task incremental domain-incremental and class-incremental settings, but it's defined based on the mapping between inputs and outputs rather than just based on the data set or anything like that. Now, that for the class incremental, you have to infer that sometimes seems a bit like unintuitive, but you can basically say that the combination of context and within context label are together defining a global label, and then you can think about it more in the way you're used to think about it. And so you see here, the same data set actually can be used both domain incremental, class incremental, task incremental. It's not given that one data set fits only in scenario. And so these intuitive interpretations we had actually match the formal definitions we have. So in task incremental, we know whether we want to play tennis or play table tennis. In domain incremental, we just want to drive and we don't care whether the sun is shining or not. In the class incremental, in the end, we want to distinguish all the categories, so we do need to know. Another point I want to stress here is that these different domains also put the focus on different challenges. Like most papers claim that the key idea of continual, or the key challenge in continual learning is to avoid catastrophic forgetting. But that's only partially true. If you have a task incremental setting, then you could just store different models for each task, and that way there's no forgetting at all. So avoiding catastrophic forgetting is not really a challenge there. The challenge is to have like sharing between part of the model so that you can have positive transfer and then still having avoid the forgetting. Likewise, in the class incremental setting, avoiding catastrophic forgetting is a challenge, but even more so, there's a challenge that you have to discriminate between objects you've never seen together before. And that's kind of a very challenging task. Now, in my view, there's too much focus on the class incremental setting and on this particular challenge and how we can deal with that we have different objects that we haven't observed before. Whereas thinking about these different views on continual learning, there's not that many settings where really this is a key issue. In a lot of the practical scenarios that people have in mind that motivates them to start thinking about continual learning, you do have overlap between distributions. And so that's, maybe we should reconsider that. That can be done by generalizing the setting a bit. So instead of having these mutually exclusive distributions where one episode is linked to one distribution only, we can generalize it by defining a context set. That's a set of different contexts, different distributions that model the non-stationarity of the data. And then we have a data stream consisting of different experiences. Experience is sampled not just from one distribution, but from a mixture of distributions. And so by this setting, we can have like more varied settings. We can have revisiting of tasks. We can have overlapping distributions and things like that. But still we have control over the amount of overlap and things like that. So we can still think about it from a mathematical point of view. And interestingly, even though this is a generalization, we can see that still you can have like these three different scenarios, these three different mappings between inputs and outputs as before. So here's an example, but for sake of time, I'll not go into detail, where we basically have overlapping distributions. And again, you can think of this in a task incremental, domain incremental, or class incremental setting. Okay, so given that one data set can be looked at from both task incremental, domain incremental, and class incremental point of view, we can then compare the same methods under these three different scenarios and see which method works best under which scenario. So again, for sake of time, I'll skip those slides, but so we looked at like 5 standard families of continual learning, and then you can basically see that indeed what works best depends a bit on the setting you're in. Typically, class incremental is harder than domain incremental, which is harder than task incremental. And if you want to do well on all 3 of them, then replay currently seems to be the best solution. Although also this template-based classification where you store like prototypes and do a kind of more like nearest neighbor comparison also works well. But that's only applicable in a class incremental setting. Okay, now apart from just defining these setups more clearly, another approach that we often see people advocating would be to say, okay, we need more benchmarks. We need more realistic benchmarks and something bigger than just split MNIST. Now, I'm not saying we should all work on split MNIST, but the same framework I just explained can also be applied on like split ImageNet or anything like that. And so provides a basis on which you can think about the data sets and the distribution shifts. If you want to have more practical, real-world challenges, then recently a couple of benchmarks have been introduced. And I think this is great because we can have different benchmarks focusing really these different views on continuous. We can have some that focus more on the reinforcement learning, like the CoLLAs that was also mentioned yesterday. We can have some that focus more on domain-incremental learning. So CLAD is a data set and challenge we introduced at last ICCV, focusing on object detection rather than classification. There's CLEAR that has like realistic distribution shifts. I get some. Yeah, okay. Yeah, there's score 50, which people already know. I think it makes a lot of sense to say, okay, I'm reconnecting. I'm not sure I'm still like on Zoom. Yeah, okay. So benchmarks are great because they also allow people to compare methods and make it more explicit, really, what is the motivation? Yeah. Yeah, I get a message like untrusted server certificate. And I said like, trust anyway, but yeah, I don't know. Anyway, I was almost done, so maybe I continue with, so they can still hear me, right? Yes. Yeah. Okay, so I'll just continue without the slides then. But yeah, so benchmarks also is something I guess should be developed further, but I think we need both. We need to have both like these real-world benchmarks as well as settings where we have more control, more academic setups, where we know what is the distribution shifts and we have better control on these things. So yeah, just wrapping it up. The main message I want to tell is let's try to be more formal about continual learning, to explicitly state what are our assumptions, what are the constraints, what are the goals, because there's a lot of different interpretations of continual learning, and this hampers progress. This makes it hard to measure progress and has a negative impact on reproducibility. And even though we say, okay, we want to go beyond solving data sets, we need to have data sets or setups that we can share and that we can reuse so that everyone can compare on the same settings. What's still missing in this picture, most importantly, is a good measure for distribution shifts, so task similarity. Now, given that a task or a context is just a distribution, you can use like measures to compare distances between distributions. And that's probably the way forward there. But nowadays, the only way, if you really want to have something about task similarity, is to switch to rotated MNIST. And that's not really a valid solution either. So doing something about measuring and ideally also being able to control the amount of distribution shift would be great to add on top of this. Also, I guess we need to have some kind of frameworks, benchmarks, and things like that also for large-scale continual learning. There's a trend towards more and more large-scale setups, and for a good reason. But there especially, we don't see a really well-structured setup that allows us to compare methods. And then you don't know whether something works better just because they started from a better backbone, from a better pre-trained model, or whether the actual continual learning idea is what helps. And that's also a problem sometimes with these benchmarks, that you optimize just for the performance, but there's many ways to get better performance just by hacking things together, doing more data augmentation, things like that, which may not be key progress in the continual learning as such. So we need to have good metrics that really focus on where we want to make progress. And I think we are far from the ideal situation there. Okay, that was it. Thank you.
For questions, please. As I said, and I'm sorry that I interrupted. Yeah, there is, of course, a need for rigorous, but the work has been done. You talked about, for example, no work on shift of the concept. There is a paper of Peter Bartlett and myself in 1996, which is called Concept Drift, and analyze it further. There is a very well-cited paper by Jonathan Baxter on learning changing distributions from 2000. There is lots of work in the corpus community, and I think a message from me to this community is there is a lot of really relevant stuff in the theoretical community. Clear definitions of distance between distributions, we talked about it yesterday. Formal models for backlog learning. Formal models for distribution shift. It is all there. Maybe it's not completely relevant to what they done today, but I really call upon this community to reach out to that, and I can send you a set of references.
Yeah, but I guess the ones you mentioned, I know which ones you refer to, but indeed, yeah, the link has to be laid, and and there's a lot of stuff there that I think we should bring in. So I think ultimately we agree.
Just to add to that, I guess to me the question is to what extent these definitions can be applied to the kind of data and processes we have, because my worry is usually when I look in the theoretical work, the definitions are too restrictive. And that's sort of the first question we need to answer. But yeah, it'd be nice to collect them and then push the community to look at them and find issues.
Hi, thanks for the talk. Question: what is one kind of scenario that you can make continual learning scenarios or settings that are very, very complex, have no past boundaries or continual reinforcement learning and so on? What are some of those settings that you think are the most meaningful to pursue going forward past these three and the generalized versions?
Yeah, so the question is like, okay, if we have this generalized setting, then we can go beyond the three settings like we had before. Which of those would be most interesting to pursue? I guess it depends on what your goal is. So indeed, for some people or some backgrounds, it might be really to go to more like data. For others, it might be more to have like overlap between like revisiting tasks and so there's not a single answer to that. I think what we should do is probably see, okay, define a couple of different settings of what people want to reach with continual learning. If it's like on the edge, or is it like scalability? And then if that setting, what could be a generalized setting where we have control, that we know if we have some continual learning methods that work on that setting, then probably they will also work well on my real world application that I have in mind. But there's too many different views on this, so there's not a single setup that would answer your question.
Thanks a lot for the talk. So I have a question. It seems like in this that we have and the ones that you presented, it's always, so we try to define which distribution changes. Is it field X, field Y, and X, or field Y? Do you think it would make sense to also look at how it changes, or maybe why it changes? So I'm thinking about disentanglement in the future, but we assume data is generated by some latent factors. We think it makes sense to think in that way and say, okay, the shift comes because there is a new latent factor, or because the combination of the way the latent factors are combined has changed.
Okay, so the question was, apart from looking which distribution changes, is how it changes or why it changes, looking more towards disentanglement. You might have different latent and then separate these out. Yeah, my first answer when you started the question was like, well, actually, we just look at it as a distribution shift and we don't care why, whether it's like the illumination that changes or something else. It's just a shift in the distribution and we want to probe how big it is or something like that. Then later, when you move on to more like the disentanglement and the latent spaces, yeah, maybe you can think about like decomposing it, and there is value in that. Obviously, if you have disentangled representations, or if you go more toward like causal learning or things like that, that has advantages in a continual learning setup. So again, that brings us to really understanding these domains or modeling these distribution shifts better. And it's, for now, we are really like in the blue there.
Hi, thanks for the talk. It makes a lot of sense for me and for the continual learning community, I think. I have maybe a simple question. It's like, what does realistic means for you? Because I feel like it's a very dangerous word that's used in many papers. And so in one thing that's more, something is more realistic than something else. So should we stop using this word, or should we use a proper definition to it?
Yeah. Yeah, so real world, I guess, is used typically like opposed to like the toy data sets or the setups where we construct data sets and settings. What is real world? Again, depends on an application. Imagine that you say, okay, I really want to do continual learning because I want to solve this application. And then your real world distributions are not perfectly one category or the other. Like it will not be mutually exclusive. It will also not be perfectly stationary. It's probably somewhere in between. And the real world is difficult to model. So and a lot of the benchmarks go towards this, in this direction of we want to go towards more real world data rather than this like well-defined and constrained setups. But there's no, the thing is that then you lose the ability to really model it, and that limits your understanding because you don't really know what the data is in a real world application, and then it becomes much more fuzzy. So yeah, I don't really have an answer.
Yeah, maybe it depends if you want to your benchmark scenario to fit an application or to be designed to evaluate something to decide. Maybe we need a bit both.
Indeed, so I don't want to really advocate for either like real-world benchmark data sets or like these more academic setups where we kind of construct data sets and problems. The latter are not real-world, and they don't claim to be or pretend to be real-world, but they allow us to develop methods and to test models in like extreme cases, and from there we can get better understanding, which we can then test and apply on the other settings. But both should go hand in hand, I guess.
Any other question? If not, I might. Oh, there's a question.
Other questions of the chat?
If not, I might have a question. So I think one question is how do we think about RL in this setting? So the description that you have is quite specific to supervised learning, but in RL, I think sometimes it's harder to talk about distribution. So it's always been a question for me whether we should yield the RL setup separately or whether there is a way to actually combine all of them together and think of them. In some sense, there's a lot of common ground, but then we can't really talk about class or anything like that when we're talking about RL. And even distribution, just because the data is conditional on the agent that's acting in the world, it becomes a bit harder to deal with concept than talking about distributional shifts and things like that.
To be honest, I haven't worked on, repeating the question. So the question was, like, how does reinforcement learning fit in this scheme? Because there's a lot of focus on classification, but then you don't have the class labels, and then how do you model the distributions and distribution shifts if you're in an RL context? Now, I haven't worked on RL myself, so it's like something far away, and it's easy to just think about classification, and then we start thinking, okay, maybe beyond classification, we should think about detection, something like that. It's true that it's challenging. I guess that's and so you don't have clear distributions, so it's indeed more a gradual shift, I guess, but you cannot define it. But yeah, I don't know. I guess it may also depend on the application. So it's too far from my expertise, really, to answer. Okay, I have to go down. Okay, how important would you say it is to maintain performance on in-distribution data set in continual learning along with out-of-distribution data sets? Well, I guess both are important, right? I guess if you have good results on the out-of-distribution, then you probably generalize better. I guess I think about it more like you have different contexts and each context has a different distribution. If you think about it as in distribution and out of distribution, it's more like, yeah, us versus the rest. And so I guess the way we looked at it so far is saying you have a few set of contexts that you want to cover, and we don't really consider out of distribution, out of these contexts. It's something that you can bring in the picture, which probably helps to generalize better, but then is your distribution just another context, another distribution, or how to define it? I don't know, but it's a good question. It's definitely something we should probably try to fit in.
Are there any other questions? If not, let's thank our speaker. And now we'll move to the